Our last topic for the semester is numerical integration. And while calculus is not a prerequisite for this course, although I think most of you are at least into calculus to some level at this point, but we'll go over a couple of concepts from calculus here that'll help us understand what we're doing a little better. Two fundamental things that we look at are differentiation and integration. That when you take a derivative of a function, you're finding the rate of change relative to a variable. And when you integrate, you're summing up the rates of change over some interval. And so we're going to illustrate that with by looking at the motion of a particle, the position, velocity, and acceleration, and how they're related. So here's a particle, and again, make the note there that in mechanics, when we talk about a particle, we're not talking about a subatomic particle or anything. We're just talking about some body that for which we can ignore the rotational motion. So we're just looking at translation, from moving from one point to the other. And to keep it real simple, we're going to look at a one-dimensional problem. So this particle is moving along the x-axis, and the position is just going to be the variable x measured from some reference point. Now, as we move over a small time interval delta t, we've moved a distance of delta x. And so we would say the average rate of change of position, in other words, the speed of the particle, is delta x over delta t. But now, when we say speed or velocity, we're talking about an instantaneous value. And so we find that by taking the limit of that delta x over delta t as delta t approaches 0, and that becomes our derivative. So velocity is the derivative with respect to time of position. Now, in a similar manner, if we're changing velocity, then the rate of change of velocity with respect to time is the acceleration. Now let's work in the other direction. So let's say that we've mapped our speed over a period of time. Based on that, can we determine how far we've gone? What is the displacement over that period of time? So going back to the equation for velocity, v equals dx over dt, and rearranging it, we see that dx is equal to v dt. Okay, so what that tells me is that for a very, very small time increment, dt, if I multiply if I multiply dt times the velocity, then I have the change in position dx. And if I want to know that over a definite time interval, I just integrate all those little v times dt areas. And so that is the definition of the integral here, is summing up all of those small increments. So we do a lot with graphs in here, and so let's take a look at the interpretation that we would do graphically here. So here's the position x plotted as a function of time. And if I look over a small time period delta t, and over that time I've gone a distance of delta x, and if I look at delta x over delta t, as this becomes a smaller and smaller delta t, then and goes to a point, you can see that the slope is going to be, in this case, the velocity. In other words, as you let the time interval become infinitesimally small, that rate of change just is equal to the slope of the curve at that certain point in time. So again, the slope at any point in time here would be the velocity. Now let's look at a graph where we have velocity plotted as a function of time. And if we look at a very small time increment, dt, and multiply that by the velocity, we get that small area that's shaded there, and that would be the change in position. But that's only for, again, an infinitesimally small area. So if we sum up all of those areas, which in other words we integrate, we sum up all those areas, we end up with the shaded area that's shown here, and that would be the change in position over that definite time integral from t1 to t2. So again, the derivative of a function is the slope. The integral of a function is the area under a curve. And with those in mind, we can now look at numerical integration. And so a lot of functions are difficult to integrate. Some of them you can't integrate. And so we can certainly get an approximate value by doing numerical integration. And again, the key to all of this is just remember that all an integral is the area under the curve of the function. So here's our first example. We've got a function y is equal to 3x squared minus 6. And we want to estimate the integral of y with respect to x for the limits x equals 0 to x equals 4. So we write it like this. Integral, again, upper and lower limits is shown there. And in this case, it's pretty easy. It's polynomial, so we can do the exact solution for comparison. Again, we do the integral, evaluate it at the limits 4 and 0, and find out that exactly 16 is the exact solution here. So here's what the plot of that function looks like. And so what we're trying to find, the integral, is just the area under the curve. Now in this case, because the curve does go below 0, there is an area of negative area and a region of positive area. So when we add those together, the the total area comes up to be 16 units. Units or whatever, based on whatever x and y are in this case. All right, so here's how we're going to do this numerically. So look at 2 points on the graph. And so 2 values of x1 and x2 and the corresponding values of the function y at each one of those. Now what I'm trying to find is the area that's under that curve. And so the easiest way to approximate that would just be to draw a straight line between those 2 points. And that's what we've done. And when we do that, we form a trapezoid. And a trapezoid, it's easy to find the area of that. You can look at it as a rectangle plus a triangle. But an easier way to think of it is, because the bottom is flat here, just think of the average height. In other words, if I average y1 and y2, and then multiply by the difference between x2 and x1, that'll give me that area. So 1/2, again, y1 plus y2, which again just gives us the average height, times the base, which is x2 minus x1, is the area of a trapezoid. So going back to our example, we're going to use 4 intervals. So we're going from 0 to 4. Each one of those will be 1 unit wide. So the first thing is we just calculate what y is at each one of those endpoints, just by evaluating y for each of those values of x. Then we draw our straight lines between those endpoints and calculate the areas. So in this case, you could see that we have a positive area over here, a total of 21, but we're subtracting off the negative area, which is a total of 3, and so our sum here is 18. Now remember what we said, that the exact answer to this is 16. So yeah, we're in the right ballpark, but obviously if we use more increments, we could get a better answer. So next time we'll pick up with this example, and we'll look at both Excel and MATLAB of how to do some numerical integration with those tools.